a bicycle ultimately is something of, a torque arm here of very little mass. And the mass of a bike is very small compared to the rider. Almost all of the rider's mass is up near the top of the bicycle. So as an object goes, we are trying to balance something heavy on something light and have it just sit there. At rest, the system has to be perfectly balanced or it'll fall. And if you've ridden a bike a lot, you know you can get to a stop and kind of sit up there and kind of inch around and keep yourself from falling, but it's not easy. Once you're pedaling, though, you don't have to do anything to stay up. And the reason, although it might not be obvious, it's that you have momentum. And because you have momentum, your inertia resists changes in motion, which includes falling that way. Now, you have to ask yourself what prevents that. Why don't you just fall over? Consider the case where in your bicycle you are leaning over. When you begin to lean over, a bunch of things start to happen that weren't happening before. There. So I'd say the center of mass is right about there. If you've been on a bicycle before, you're probably right. If you're leaning up higher, you bring the center of mass up. If you're leaning down low on the handlebars, you bring the center of mass down. Watch professional motorcycle drivers on a course. You'll note that they can typically get their center of mass very low on the bicycle. There's advantages to doing that. Now, consider the forces in this system. There's going to be an upwards force from the ground, normal force. There's going to be a downwards force of weight from you. These may or may not be balanced. They're probably not. Well, I'm sorry, they will have to be balanced, or else you sink or rise up. But there is wiggle room for a bit of imbalance, and it has to do with the fact that there's another force this way. The forces have to be in balance up and down. They do not have to be in balance left to right. I'm saying that because if the bike is like this, it's turning. Right, you're turning to the left. There's an unbalanced force to the left. Thus, this bike can turn to the left. Now, the frictional force comes from static friction still, which means it's based on the normal force. Normal force is the weight of the object. Now, if you want to actually turn, we want the net force to be equal to MAC. We want the net torque to be equal to 0. Right? We do not want the system to twist or turn. We don't want there to be an angular rotation. So we need the torques to balance, but not the forces. This is how a bike turns. You cannot turn your bicycle without leaning. Thus, the training wheels screw you over. Because that's where the training wheels play a role in causing you to tip. Training wheels throw this all out of balance. Now, the real thing is how far can you lean and still turn your bicycle? The truth of the matter is, there are some limiting factors here. There's going to be a certain amount of friction required not to make the turn, but to bring the system in balance. Right? If we look at the pivot point is perhaps here, which means if you use that as your pivot, only this force is one that has to be balanced for your torques, but we need balanced torque. We want the net torque to be 0. So in calculating these forces, you'll realize this is a complicated system. We can do this calculation after a couple of days. You need a little more training. Well, we can figure out the optimum angle to lean your bicycle to make the turn. By the way, though, this whole system also is a centripetal system, and because it's traveling in a circle. Thus, we should do a top-down look at it too when we actually calculate this problem. So, if you've ever ridden a bike before, don't think about any of this stuff while you're driving it. or you'll fall. Especially if you go to make a turn and you start thinking about how far can I lean it and still be able to stay upright. You'll fall. Please try this weekend. It could be fun for all of us. Have somebody video it. All right. Let's stick with some relatively straightforward ideas because the idea of the bicycle might be a little too much. Yesterday we did the Atwood machine. We did a ball rolling down a ramp. Today we're going to do something a little bit different. I want you to think of like a bar, meter stick, something like that. That is attached here. So it has a pivot point that's located at one end. And I'm going to hold it perfectly horizontal. Now, it shouldn't be a surprise that if I release one end and hold the pivot point, that it's going to swing downwards. Well, when it reaches the horizontal, when it reaches the vertical, a little too long. When it reaches the vertical, it's clearly going to have some angular speed. My question for you is, what is the linear speed of the bottom of the meter stick? Now, let's assume this bar, I said meter stick, but let's say it has length L and mass M and can be considered a rigid bar. It might not seem obvious, but this is a conservation of energy question. And it's based on the fact that the center of mass of the bar is going to move from one place to a lower location. So my first discussion point, the thing I said yesterday, is when you're trying to figure out whether you should use energy or not, you're looking to see if the object changes height. By definition, this object is fixed in space. It's got a pivot point on one end. It's not going anywhere. But does the center of mass of the object change height? And in this case, the center of mass of the object goes from a location here to a location here. So the object's center of mass changes height even though the object is fixed in space. Because its center of mass changes height, there's a change in potential energy. In fact, when the object is located at its highest point, it has energy mg L over 2. And this is due to the fact that the center of mass can go to this position here. Its lowest position is half the length of the bar. Now, before I go on, does everybody understand where I got the gravitational potential energy from here? We're good? Well, if I assume that when it's perfectly vertical, it has converted all of its potential energy to kinetic energy, then I can set this equal to 1/2 I omega squared at the bottom, where all of its energy here is in the form of kinetic, rotational kinetic energy. This object does not have translational kinetic energy if I assume that the pivot point is still a fixed location in space. It is pivoting around that point. Now, although I'm still recording this, what I'm really going to try and impart to you is something that is going to be confusing in the beginning. And it might even be confusing right now. And that is, how do you know when the object has translational kinetic energy versus rotational kinetic energy? And there is a huge indicator of when you can do that. If it has got a fixed point in space, if you can't take the entire meter stick and move it someplace else, then it never has linear kinetic energy. It's all rotational because it's got a fixed point that stays in place during the whole time it's moving. Now, here's where I'm going to hit the... This object has a fixed point here, which means the object never actually leaves that location. Under those circumstances, it's almost always, in fact, I could probably throw out the almost and say it's always better to think of the rotational kinetic energy of this object. Otherwise, different pieces of this object have different kinetic energies. If I start moving that pivot point farther away from the object, that becomes a little more gray. The gray area gets bigger. So don't just think of this as one or the other. Approach it from how could I best serve the needs of this problem. This bar has, though, one amount of energy. It's how you express that energy that's important. I can express it all in the terms of 1/2 I omega squared when it reaches the lowest point of its center of mass. So, at this point, if I want to find out how fast it's going, I think the starting way to do that is to figure out what its angular speed is. So, getting back to that, I have mg L over 2 equals 1/2 moment of inertia of a bar about an end. Is it 1/12 or 1/3? 1/3. It is 1/3. It's the larger of the two because it's about its end. All right, algebra. Get rid of them pesky m's. I'm thinking I can get rid of the 1/2. And that leaves me with omega equals the square root of 3g over L. If you don't believe me, do your own math. Now, whenever you get something like this, take at least a second and make sure your units work out. I have the radical of meters per second squared over meters. This is going to leave me with nothings over seconds. Radian is a unitless quantity. That's the answer. So my units work out. That gives me high confidence in my answer. Of course, that was not the question. The question is, what is the linear velocity of the end of the rod? At the end of the rod, the linear velocity is the angular velocity times the length of the rod. So, the angular velocity times the length of the rod. So, you guys do the math. L squared, put in the radical, cancel one of the L's, gives you this. Yeah, I'm expecting you to do that. That's what AP is going to expect you to do. The most reduced state is the best answer. Also, I want you to kind of think this through a little bit. Use a little more of your spidey senses to work this out. Square root of GL, how many times has that shown up this year? Every time we've dropped something. If you drop something from yay high, it reaches the ground at square root of 2GH. Every time. Do you guys see why I'm telling you to use that now? The speed at which the speed acquired by an object because gravity accelerated it is going to have this root of GL in it. Root of GH, root of GX, something that indicates how far it fell and how much acceleration was due to gravity. That's why we see it show up so often. So when you see it, have confidence that that's probably the answer. The part that's hard is whether the 3 was the right number or not. The GL is not going to be your thing you're contesting. All right, what do you think? Hard or easy? Now look, it's not this problem I'm worried about. This is not going to be the problem on the exam. This is going to be part A of 6 parts. Because when it reaches it down here, it's going to hit this block. When it hits that block, they both stick together. What is the new height of the meter stick? or it's going to hit that block and they're going to separate. What's going to be the speed of the block after they separate? This is just one part of a larger problem. It is very likely that you'll have a problem that's going to combine conservation of energy with conservation of momentum. The bullet strikes the block problem, but in angular form. So we learned a little bit about the energy stuff today. If you look back at it, the force acting on it is gravity, causing a torque. The problem is that when the bar is here, the force might be the same, but that angle keeps changing. Not going to be able to use forces here. Not at all. The problem we have is that that problem could not be solved using forces. There's absolutely no way to do so. Cases, however, where we're going to have to resort to dealing with force, where the only way to solve the problem is to calculate the torque that's acting on our system. And let's be honest, although we talked a little bit about it at the end of last semester, torque complicates matters a bit. It's whenever we use a force to cause a twist or a turn of an object. Torque, lowercase tau, is R cross F. R represents the distance from the pivot point, F the size of the force. They're both vectors, which means I have to take into account this angle, which is why R cross F is RF sine phi. This is how to apply a torque, the how portion. This is what you have to do to cause a torque. Now, we know the result is going to be an acceleration. Let's go all the way back to the beginning of the year. If you want to move something, you apply a force. How it responds depends on its inertia. If I want to turn something, you apply a torque. How it responds depends on its inertia. Remember, inertia is the number one idea in physics. If you understand it, you understand physics. If I want to cause this object to rotate, how it responds to the torque is all about the shape and distribution of the mass. The difference, and this is an important piece, and we're not in AP Physics 1 any longer. An important piece here is that we now know that the shape of the object determines how it responds to the torque, but the shape of the object sometimes dictates how you can apply a torque. You combine that, you can come up with some interesting questions, because sometimes the best way to turn something isn't the best way for it to be turned. I know it sounds odd, but think of it. The best way to turn a lot of objects we come up with is often something that we have to spell out for you. We put door handles on the doors, because the best way to turn it is by pushing as far to the edge as possible. However, we put the hinge not in the middle of the door because we don't want it to turn in the middle. It'd be easier to turn the door if the hinge was in the middle of the door, right? Lower moment of inertia. But then it'd be hard for many of us to get out of the door if it turned in its middle. So we have to put the hinge at the end to make the doorway as big as possible. Now, I'm kind of joking around using the door as the example, but understand that if I'm trying to come up with a problem to ask you guys, manipulating these things is the first thing I'm going to do. Manipulating where you can apply that torque versus where the pivot point is. Heck, if you just lay a bar on a frictionless surface, if I kick it in the middle, if I apply a force right at its center of mass, that's no big deal. Right? Give it an impulse, the whole meter stick is likely to start moving upwards. Now, if I kick it over, say, here, you understand that the whole meter stick's going to move, but the whole meter stick's going to rotate. It's not going to stay in place because there is an unbalanced force. So its center of mass is going to start moving this direction. But it's probably going to pivot we're probably going to have to figure out how much torque was applied to this object. So, we talked about torque. Begin looking at the questions in the book on torque and how objects respond to an unbalanced torque. Next week, Monday, the Earth-Sun system. If I put the Sun here and the Earth here, the Earth has a tangential velocity at this instant. What kind of energy does it have? Does it have translational kinetic energy, or does it have rotational kinetic energy? And I'm not talking about the fact that the Earth is spinning. I'm talking about just its motion around the Sun. And here's the important point. It doesn't have both. It has one or the other. Its translational kinetic energy is 1/2 mass of the Earth times its linear velocity squared. It has rotational energy given by 1/2 the moment of inertia of the Earth relative to the Sun times its angular velocity squared. But the Earth is considered a point mass relative to the Sun, which means that its moment of inertia is me times r squared, where r is that distance. Right? This is the distance between the Earth and Sun times omega squared. But omega is its linear velocity divided by r quantity squared. Right? Well, come on, guys. It's the same thing. So, the reason I bring this example up is there's a gray line between these, a gray area. You don't have to think of things as both having just one or the other. If it's to your advantage to consider the rotational scenario, then use the rotational scenario. If it's to your advantage to use something that's more linear, then use something that's more linear. I mean, your situation should dictate the best way to approach the problem, but we derived rotational kinetic energy from linear kinetic energy. This is still the most basic form of energy that exists. We derived this by looking at a rigid object who has bits of mass moving all over the place. You start looking at your systems, though, you can apply one that works for you or works best in your system.